In what ways is a larger group constructed out of its subgroups? If we really want to understand that question, we're going to have to come to grips with the fact that not all subgroups of a given group are created equally. Some of them are window dressing. Some of them are like load-bearing walls in the house that is the group. If we want to understand how groups are built out of their subgroups, we need to identify which are the load-bearing subgroups, not just the bricks, but the building blocks on which that group is constructed. These are called the normal subgroups. And in this video, we want to understand how to recognize them when we see them, and then what is an appropriate definition for what it means for a subgroup to be normal. The guiding principle that's going to determine whether or not a subgroup is capable of being a building block for the larger group is whether or not the cosets of that subgroup themselves have a group structure inherited from the larger group. In other words, can the cosets be a group in and of themselves? And it might sound like an easy thing to satisfy, but it turns out it's not really the case. And the reason is that the cosets of a given subgroup are not elements a priori, they're sets. And so each coset is going to have a bunch of different elements in it. And in principle, those elements can behave quite differently from one another. What we don't want is for the differences within a given coset to be reflected in the structure of the group that we're trying to make out of those cosets. In other words, the elements within each coset have to be similar enough to one another that under all circumstances in that factor group, they act identically to one another. That's the bar that we have to set for ourselves. That's the hurdle that we need to clear in order for our subgroup to be a normal subgroup. So in this video, we'll illustrate what normal subgroups look like and what they don't look like, just by using an example that will lead us to the definition that we want. So inside the symmetric group, permutations on 4 symbols, here are 2 different examples of subgroups, each of which has order 4. I call them M and N. And what I want to do is highlight the essential differences between M and N in the role that they play within the larger group S4. To get that started, let me list all 24 elements of S4 and highlight how the cosets of M and the cosets of N constitute those 24 elements. So here in the first example, M is my subgroup of order 4, and here in the rows of this first table are the 6 cosets of M, which we can get by obtaining multiplying by 1, 2, 1, 3, 1, 4, 2, 3, and 3, 4. In my second table, same thing, just with the subgroup N instead. And here, to account for all the cosets, I'll multiply by 1, 2, 1, 3, 1, 4, 1, 2, 3, and 1, 3, 2. So all I've done here is I've listed all the cosets of each one of these subgroups inside of S4. And the question, remember, is, can those cosets act like a group themselves? In order for that to be the case, I need them to act like individual elements. In other words, I need to be completely blind to the differences between different elements in the same coset. For example, if I take the element 2, 4, which is representing the 3rd row here, and I take the element 1, 4, which is representing the 4th row, if I multiply those 2 elements of S4 together, their product is 1, 2, 4, which is an element of the 6th row. So if these cosets are to behave like elements in and of themselves, then what needs to be true is any element of this 3rd row, the coset 1, 3M, multiplied by any element from the 4th row, 1, 4M, needs to give me an element of the 6th row, 2, 4M. This entire row multiplied by that entire row has got to account for this entire row. So we need to not be able to tell the difference between different elements in the same coset. Does that hold for this subgroup? To figure out, let's just try another product. Instead of 2, 4 times 1, 4, I'm going to change 2, 4 to a different element in the same coset. Let's change it to 1, 3 instead. What do I get when I multiply 1, 3 times 1, 4? If these cosets are behaving like a group in and of themselves, that means that I should get the same coset when I multiply 1, 3 times 1, 4 that I got when I multiplied 2, 4 times 1, 4. But that's not the case here, because when I multiply 1, 3 by 1, 4, the product, 1, 4, 3, does not land in the 6th row, it lands in the 2nd row. So the differences between different elements in the same coset of M matter when the subgroup is chosen to be M. And so this subgroup M is not a subgroup whose cosets are going to form a group. We can't even get the cosets to behave coherently with one another. I pick different elements in the same coset, and it changes my product. So M is not the kind of subgroup that we're going to want to work with. We cannot build our group on top of M as a constituent subgroup. So this is a problem. Ultimately, the normal subgroups, the ones on which we're going to be able to build our larger groups, need to not tell the difference between different elements in the same coset. Differences within the same coset need not to matter. So let's check what happens when the subgroup is N and the cosets are cosets of N inside of G. If I multiply 2, 4 by 1, 4, once again, I get 1, 2, 4. So again, I'm in a situation here where the third row multiplied by the fourth row lands me into the sixth row. But now if I vary my elements inside the same coset, for example, doing 1, 3 times 1, 4 again, well now 1, 3 times 1, 4, 1, 4, 3 also lands in the sixth row. And if you feel like doing more operations in the symmetric group, you can also check 1, 4, 3, 2 multiplied by 1, 3, 2, 4 also lands me into that sixth row. And in fact, any element from this coset, any element from the third row, multiplied by any element from the fourth row, is always going to land me in the sixth row, regardless of which elements were chosen from the third and the fourth row. Any element can represent its coset, in other words, and give us a coherent operation. So those differences within each coset don't matter to that operation. And those are the kinds of subgroups that we want. Those are the ones on which we're going to be able to build a larger group. Those subgroups that have this property, so N is going to be such an example, are called normal subgroups. When N is a normal subgroup, it means that any element from one of its cosets multiplied by any element from another of its cosets are going to always give me an element in the same product coset. And in fact, that product coset can be taken to be represented by the product of the elements that represent the first cosets. After all, if that representation doesn't matter, then any element from 1, 3n multiplied by any element from 1, 4n is going to necessarily give me an element from 1, 3 times 1, 4 times n. In other words, the coset of 1, 4, 3. So that's ultimately what we want out of this whole process, is we want our cosets to act like a group, but we end up getting more than we asked for, because those representatives of the cosets will also multiply together in a coherent way. So any element of 1, 3n multiplied by any element of 1, 4n is going to give me an element of 1, 3 times 1, 4n. In other words, 1, 4, 3n. So what is the right definition in order to make sure that this happens for a given subgroup inside of a given group? Motivated by this example, if I want 1, 3n multiplied by 1, 4n, and this multiplication is happening as sets, right? So I'm taking an arbitrary element from this coset, the purple row, and an arbitrary element from this coset, the orange row, and I'm multiplying them together. I'm getting an element inside of the yellow row. But how to account for this 1, 4, 3 showing up? Well, we can do that exactly because 1, 3 times 1, 4 is equal to 1, 4, 3. But that's only going to happen when the product of two cosets and the coset of the product coincide. If I want 1, 3n times 1, 4n to be equal to 1, 4, 3 times n, that means in general I want AH times BH as sets to be the same set as AB times H. The product of the two cosets needs to be the coset associated with the product of those two elements. When that happens, then my subgroup is called a normal subgroup. And that's precisely the condition that we need in order to guarantee that the cosets of this subgroup themselves have a well-defined operation that makes them into a group in their own right. To make that into a formal definition, let's just look a little bit more closely at what's going on. We'll say that H is a normal subgroup of G, and we'll use this little triangle. So it's like the subgroup symbol, but we close it up into a little triangle, H triangle G. We're going to say H is normal in G if, for any elements of G, A and B, the cosets associated with A and B of H, so AH multiplied by BH. When I multiply those cosets together, I get the coset associated with the product, AB times H. So any element from the coset AH multiplied by any element from the coset BH is going to give me an element from the coset AB times H. So under what circumstances can we expect for that to happen? Well, in order to get the A and the B together in this expression, what I really need to be able to do is to trade places. If I had a situation in which any element from H, my subgroup, multiplied by B, also happened to give me an element from the coset BH. If I could trade places, if I could move this B past this H, in other words, if the right coset associated with B and the left coset associated with B were the same set, then we would be all set to go. We'd be able to trade places with this H and this B, and we would get AH times BH is AB times H times H. But because H is a subgroup, it has a closure property, and therefore H times H as sets is the same thing as just H. So if the right coset of B and the left coset of B are guaranteed to be the same, then we know for sure that my subgroup is going to have this property. And indeed, that's how we define what it means for a subgroup to be normal. A subgroup H is normal in G if any element of G's left coset is equal to that same element's right coset. G times H is equal to H times G. So in other words, every element that can be written as G times an element of H, so anything that I can write as G times something from H, can also be written as something from H multiplied on the right by G. Now keep in mind, these two elements don't have to be the same, because we're just making an equality, an assertion of equality of sets here. We don't have to say, for example, that G times X is equal to X times G for every G in X. That's too strong of a statement. Clearly, if we have an abelian group, or if G belongs to the center of our group, then we'll be all set. But that's more than we need, really, for a normal subgroup. Because the element from H, which makes an element GH over here, doesn't necessarily have to be the same element that makes the HG on this side. But every element from this coset has to also be some element from this coset as well. So here's a theorem that we've seen proven before that actually is going to help us in our search for when normal subgroups exist. So how do we know that there are any normal subgroups in the world at all? One quick theorem is we know that any subgroup that has an index of 2 is guaranteed to be a normal subgroup. So if the index in G of the subgroup H is equal to 2, then automatically H will be a normal subgroup of G. Why should this be the case? Well, I'm only including this proof here because it's such a quick proof. If we imagine that H is an index 2 subgroup of G, and I pick any element in my group, G, then H divides my group into two pieces. H itself, the subgroup, and then also the one unique left and right coset of H, which is the same thing as the complement of H in G. So if I pick an element G which belonged to H in the first place, then when I multiply G times the set H, if I form the left coset or the right coset, because of closure, I know that those cosets are going to be the same as the subgroup themselves. So if I pick G to belong to my original subgroup, then GH, the left coset, and HG, the right coset, are both equal to the original subgroup H, just again by closure. If I pick a G that doesn't belong to H, then I know for sure that GH is going to be not equal to the original subgroup. And because cosets are either identical or disjoint one to another, we can't have them partially overlapping one another. They either overlap completely or they're completely disjoint. If G doesn't belong to H, that means the entire coset of G doesn't belong to H. But the entire coset of G, whether it's a left coset or the right coset, because there's only one copy of H that's left over, that's not accounted for by H itself, those cosets are exactly equal to H complement, and therefore they're equal one to another. So every subgroup of index 2 is guaranteed to be a normal subgroup, regardless of any other structure that's happening within the group. So we know now that this is not too much to ask, right? That even for really scary groups out there, for example, the symmetric group on any number of symbols, always has an index 2 subgroup, namely the alternating group on the same number of symbols. AN is an index 2 subgroup of SN, and therefore AN is a normal subgroup of SN. So normal subgroups do exist out there in the world, and we recognize them by their left cosets being equal to their right cosets. Another way to say what it means for a subgroup to be normal is to say that the subgroup is closed under the operation of conjugation. Remember, conjugation means taking an element and multiplying it by the same element on the left and the right-hand side with an inverse on the right-hand side. So to conjugate an element by G means to multiply it on the left by G and on the right by the inverse of G. And if we look at this definition a little more closely, we'll see that what it's saying is that H is a normal subgroup in G if and only if, when I take an element from G and I conjugate by that element something from H, the result remains in H. So if you give me an element of H, I can conjugate that element by anything from my whole group, and the result is going to remain inside H. So normal subgroups are subgroups that are closed under conjugation by any element from within the larger group. Any conjugate of an element of H is going to remain an element of H. So there's another way to understand what's happening inside of a normal subgroup. And here's a quick proof of that. If we first assume that H is a normal subgroup of G, then I pick up an element arbitrarily, any element G inside of my original group. How do I know that this statement is going to be true, that conjugation by G is going to remain inside of H? If I want to prove that this set is a subset of H, then I just need to pick an element in this set and show that it belongs to that one. So let's let X belong to G times the subgroup H times G inverse. By definition, that means that X is equal to G times H times G inverse for some element H which belong to my subgroup. But if X is equal to GHG inverse, then multiplying on the right by G, we find out that XG is equal to GH, and therefore XG is an element of the left coset of G by H. But on the other hand, we assumed that H was a normal subgroup in G and therefore meets the definition at the top of the screen. Therefore GH and HG are the same. The left coset and the right coset are the same. Therefore, XG belongs to HG. So for some H, now not necessarily the same H, so H prime, for some H prime in the subgroup H, XG is equal to H prime times G. But then, rearranging this equation finds out, just by cancellation property, and cancel the G's, find out that X is equal to H prime. But H prime, by assumption, belonged to H, and therefore we've shown that if I pick any element X from this conjugated coset, I've now discovered that because H was a normal subgroup in G, X belongs to the subgroup itself, H. So there's the forward direction. To get the backward direction, let's assume that this subset relationship holds, right? That my subgroup here is closed under conjugation by any element of the group G. If we make that assumption, then we need to show H is normal in G. So I need to choose an arbitrary element of my group, capital G, and show that the left and right cosets of H by that element are the same. To do that, I'm going to pick an element in the left coset, GH, and show that that element also belongs to the right coset, HG. I would also have to do the other way around. If X belongs to GH, that means X is equal to G times some element H from my subgroup. But if I multiply on the right by G inverse, I find out that XG inverse is equal to G times H times G inverse. But G times H times G inverse is an element, by definition, of this set here, G times capital H times G inverse. But by assumption, that's a subgroup of H, subset of H, sorry. And therefore, XG inverse must therefore also belong to H. And if XG inverse belongs to H, that means it's equal to H prime for some element H prime in my subgroup H. And then by multiplying on the right by G, I find out X is equal to H prime G. Therefore, X belongs to the right coset HG. So I picked an element in GH, and I showed, based on this assumption, that that element belongs to HG. The argument going in the opposite direction is completely analogous. And therefore, we can prove that GH is equal to HG. So in this video, we've just talked our way into the definition of a normal subgroup. Normal subgroups are the kinds that we like because we can build the larger group atop of its normal subgroups. The reason is that the cosets of a normal subgroup themselves form a group called, as we'll see in the next video, the factor group associated with that normal subgroup. And the key secret sauce to making that happen is that a normal subgroup is exactly a subgroup whose left cosets by an element are equal to the right cosets by that same element. GH is equal to HG. Or another way of understanding that is that the normal subgroups are the subgroups that are closed under conjugation. That if I conjugate an element from H by any element from my larger group G, that the result is going to remain within G. Normal subgroups are our key building blocks to understanding how to break a group apart into its factors, and its factors are what we're going to look at in the next video.